So, up to this point, we've talked quite a bit about the theory that's going on inside of the column, especially, because the column is the most important part of this process of chromatography and the most important part of the instrument itself. So, that's why we've taken, a couple of videos now to describe this process that's happening at the chemical level. And we ended up in the past video with this C18 and C8 discussion. So what you're seeing on the screen is your modified silica. So if we've taken silica and we've created this network, right, the silica particle inside of the column, well, silica was polar, and we said that's bad news because most of what we run all the time is a nonpolar compound. So we're going to have to modify the silica so that way it will be attracted to these compounds that come through. So we modify it by adding carbon 18 chains or carbon 8 chains to them. And what you're seeing up here at the top is that this was an OH group, an alcohol group, right? Go back and take a look at that silica structure. You're going to see OH up at the top. We've modified that OH through a series of reactions, and we've taken the hydrogen off and we've replaced it with an 18 carbon chain. So this is a C18 column. That's what we would call that. So that stationary phase is silica based, but it is a C18 column because this C18 is hanging off of the particles, and those are the arms and the fingers that these compounds will see as they travel through the column and begin to get held back. So that's the whole point of C8 and C18 columns. It's all about the attraction here. That is what we're after. Okay, so we need to talk more about what's happening inside of this column. And a new word is going to come about. And this new word is called adsorb. Okay, over to the side, I'm going to write a new word. Absorb. These two are not the same. Okay, I can't stress that enough. These two are not the same. Adsorb is different than absorb. So you got to be careful in the way that you say it and the way that you write it. Don't get them confused. If something absorbs, that means it engulfs it, right? Or it takes it in. Adsorb is different. It does not engulf anything. It doesn't take it in. The only thing that adsorb does is that it sticks. Okay? It has a sticky surface, and this compound lands on this sticky surface, and it takes it a little while, but it's eventually going to leave that sticky surface and go on. If the molecule was absorbed, the molecule would actually be engulfed inside of the particle, and that is not what goes on here. So absorb, if I wanted to draw a picture of what's going on, if something absorbs, we've got this silica base with these hands and fingers that are coming off of it, and I got a molecule. The molecule comes into the picture and it says, ooh, look, these hands look inviting, these fingers look tempting, so I'm going to go and hang out on this particle for a while. And if the particle is absorbed, it actually goes inside of the particle and it stays on the inside. Okay, this is not what happens in chromatography. That is a problem. We don't want anything absorbed through the process, right? We just want things held back. We don't want things to go into the tunnel and stay in the tunnel forever. We want it to eventually leave so we can collect it and measure it. So absorption is not the process that we want. What we want is adsorption. So what happens here is that we've got a particle and a molecule that comes into the picture, and the molecule looks at this and says, ooh, tempting fingers and hands. I'm going to come over here and hang out for a while. And the particle doesn't engulf it. These hands and these fingers just kind of give that molecule a nice massage, and that molecule hangs out while it's getting its rub down, and that molecule finally, eventually, says, okay, you know what, I can't stay at this massage hour forever, so I'm going to leave now. Bye-bye, thanks for the massage. And it goes back off of the particle. And then what happens is that it's driving home and it sees another massage place by the side of the road, and it says, you know what, that felt really good just a couple of minutes ago. So I think I want another massage. So it stops by that massage place and it gets a rub down and it enjoys its time while it's there, but it doesn't stay there forever. And that molecule dislodges back off, and it goes and it tries to make its way back home, and it keeps doing that over and over and over. I like to call this the game of Plinko. If you've ever watched Bob Barker, and now I'm giving away my age, on The Price is Right, you will see this game of Plinko. And it will kind of, this token would kind of start up at the very top of this board, and it would hit a series of nails as it went down, and it just kind of bounced in all random directions as it went down to the bottom. And then wherever that token landed in the very bottom, that's the prize that you won. It could have been money, it could have been a trip, who knows, but that's the prize that you won in the game of Plinko. Well, this is our game of Plinko in the column. This token is the molecule that we're looking at that we want to measure, and it's hitting a series of silica particles as it travels through the column one by one, and it's getting held behind a little bit. Its trajectory is getting changed a little bit, but it's eventually, slowly but surely, making its way through the column. And that is what we call absorption, not adsorption, right? It doesn't engulf anything, it just sticks to the surface. So this is a diagram, maybe a little bit better than what I can draw, that shows you adsorption chromatography. And this is how HPLC works. This is how it's based. So all of these are molecules of interest that you want to separate from each other. And these molecules are exposed to the surface of the silica, whether it has C8 or C18 or something else on the surface. It's exposed to that surface, and they hang out for a while, and we call that they are adsorbed on the surface. So they are there, but they're only there temporarily. They are not permanently attached. So they will begin to travel down the column, and they will begin to hit other fingers and other hands along the way until they come out of the very other end of the column itself. And that is what we call adsorption chromatography. We often also use this word called affinity. The molecules have certain affinities to the stationary phase, meaning affinity, if you have an affinity for someone, you like them, right? And the molecules like the stationary phase at different levels. Some love the ground that they walk on. Others, well, they're okay if they go out to a movie or to dinner with them, but that's about it. And then others will turn the hallway and run when they see the other one coming around the corner. So those are different affinities or attractions that the molecule and the stationary phase has with each other. So they are there temporarily, not permanently. They do get dislodged and get kicked as they go through the column. Now the question here is, what kicks them off? right? So that's the purpose of the mobile phase. And that's why we constantly need to add liquid into the system. Because if we don't constantly add liquid, then this molecule could maybe hang out at the masseuse a little bit longer than that we're supposed to. So you need to call it up and say, honey, why ain't you home yet? Right? Dinner's on the table. I'm waiting. Well, that's the purpose of the mobile phase. It's that phone call. The mobile phase keeps kicking the molecules through the column. And if the mobile phase stops getting introduced, then the molecules quit getting kicked from particle to particle, and the molecules stay in the column for a very, very long period of time before they come out. So that is why we constantly have to give the instrument water or mobile phase in order so it doesn't go thirsty. Because when it dries up, the whole separation stops as well. So that's the story with absorption. It's all about the attraction and the affinities here. That's really what this is all about. It's about polarity, non-polarity, attractions with the two molecules together. How do they hang out on the surface of the particle? How long are they hanging out? What are they doing while they're there? And what type of mobile phase is coming into the picture to kind of shove them on along through the tunnel so they can go out of the other end. So here's a nice little cartoon, and it says, I can't go out with you again. There just isn't any chemistry between us. Okay, so, if you've got that googly-eyed co-student that's in your class that is maybe your lab partner and, that maybe has that small crush, well, maybe you can use this line on them. I'm sorry, there's just no chemistry between us. Sorry. So they would enjoy that. They would appreciate it. At least you're honest. Okay, so that really ends the whole theory part of the HPLC instrument. So in the next set of videos, what you will see is us focusing on the pieces and parts and what makes this machine up. So terminology, polar, nonpolar, stationary phase, mobile phase, elution, right? C8 and C18 columns, methanol, acetonitrile, all of these are brand new terms maybe that you have never used before. So there's quite a bit of different definitions and quite a bit of stuff that you've learned hopefully throughout this theory portion of the HPLC instrument. And don't be surprised if some of these questions do not show up on that Chem-Tech-a-thon exam that you'll take on the last day of the competition. It'll be multiple choice, but at the same time, we want to prove that you're learning something in this process, right? So that's the purpose, one of the purposes of the Chem-Tech-a-thon examination that you will take at the very end. Don't stress out about it. It's not for a grade, but it is just to tap to see how much you really are taking away from this learning experience that you are going through with the Chem-Tech-a-thon competition. So this setup, before we leave, if you've got a stationary phase that's nonpolar, and if you've got mobile phases that are polar, like methanol and water and acetonitrile, that particular setup is called reverse phase chromatography, and sometimes that's abbreviated as RP-HPLC. So reverse phase HPLC. Reverse phase means that your polar substance is the mobile phase and your nonpolar substance is your stationary phase. So your compounds are hanging out with the stationary phase for quite some time. And the mobile phase is just the push that's making these compounds go from one particle to the next until it leaves the column out at the very end. So that's what we call RP-HPLC, or reverse phase chromatography. All of the HPLC methods that you will use, that you will do will be reverse phase. The other alternative is called normal phase. Yeah, it's one of those things where normal phase is not normal. Normal phase is how chromatography first began, and then after we realized the use of it, we realized that ideal scenario is not perfect. We're going to have to flip it. So hence we flipped it, and we got a polar mobile phase and a nonpolar stationary phase, and that's called reverse because we flipped it. But that is what we typically see in a laboratory on a daily basis. That is the most common setup. So, hopefully I've not bored you too much. Hopefully you've learned something from the theory of general chromatography. And now we need to go in and talk about the instrument pieces and parts. So that's what you'll see in the next set of videos. It will be the HPLC instrument that we have in our lab, and we're going to go through and we're going to talk about the pieces and parts of the equipment and why it works the way that it does and why it's there. Finally, after the pieces and parts, we will then look at software. We'll walk you through the software because it is fairly complicated, and we'll show you some of the screens and some of the options that you need to be aware of when you run a sample. So that's what's coming up. Now is a good time to take a break if you've not taken one yet. You've had over an hour's worth of videos so far. Don't cram it all into one sitting, right? I know you're excited. I know you want to get to the equipment. I know you want to get your hands on stuff. But take your time. Enjoy it. Be a sponge. Absorb it.